Welcome to the Explainer. So, you might want to put on your structural detective hats for this one because today we are completely dismantling everything you thought you knew about the fabric of reality. We're setting the stage for a massive paradigm shift, moving completely away from mainstream physics.
Imagine for a second, what if the fundamental nature of what you perceive as physical reality, the probabilistic clouds, the shifting particles, all that uncertainty, what if it's actually just a trick of the light? What if this entire fuzzy quantum realm is an illusion created entirely by the limitations of our own measurement?
Section 1. The Fuzzy Quantum Illusion. To really grasp how we might be getting reality totally wrong, we first need to look at what mainstream physics accepts as the absolute truth right now. Okay, let's dive into this. The established view of quantum mechanics basically tells us that reality is a fuzzy, blended smoothie of probabilities. According to Heisenberg, things exist as these vague probability clouds. And instead of using normal classical numbers, like, say, 5 or 11, quantum mechanics uses what they call Q numbers. These are complex tables of matrices, where the order in which you multiply them actually changes the result. Because of this, mainstream physics argues that deep down, particles can exist in superpositions, and when they're separated, they supposedly communicate through that mysterious, spooky action at a distance we call entanglement. Well, get ready, because we're about to pull the rug completely out from under that fuzzy view. Break through alternative frameworks, like the finite observer theory, propose a radically different foundation. We're talking about a rigid, exact, deterministic substrate. A reality that is entirely verbless, with absolutely zero fuzziness. And that brings us to Section 2, the deterministic substrate. Let's peel back the curtain and see what this rock-solid reality actually looks like. Think about models proposed by prominent physicists like Gerard-Hooft, which are based on cellular automata. In this view, the universe operates via fixed, local rules on a discrete lattice. There is literally zero fundamental randomness. No wave functions magically collapsing just because someone decided to look at them. It's entirely deterministic, built from the ground up on perfectly defined real states. Researchers actually formalize this as a tensor network. It's a fundamentally static, discrete, n-dimensional architecture of relational, informational degrees of freedom. Now, what does that mean? It means it doesn't evolve over time. It is a verbless, unchanging, geometric crystal of pure information. This structure, the Wheeler-DeWitt bulk, forms the true, unbending foundation of absolute reality. But hold on. If reality is actually this rigid, infinite-dimensional crystal, why on earth do we look around and see a fuzzy 3D universe that moves through time? Great question. Section 3, the finite observer bottleneck. Think of it like trying to shove an entire ocean of information through a tiny garden hose. Wide, highly complex structural data from that tensor network geometry gets squeezed through a narrow constriction, a bottleneck, before it projects out into our continuous reality. And here's the kicker, that bottleneck, it's you, it's the observer. But we aren't talking about a conscious human in a lab coat here. Actually, scratch that. An observer is simply a finite informational agent. Any finite system is strictly constrained by a finite Shannon information capacity. Mathematically, they call this COBS. You simply do not have the memory or the computing resources to process the entire infinite crystal. So it becomes a simple math problem. If the complexity of a system you're interacting with is lower than your capacity, you track it perfectly. But the exact moment the system's complexity exceeds your finite capacity, your memory completely saturates. Because your boundary can't hold all that data, you are mathematically forced to drop information. The sources refer to this as a dimensional partial trace. Our fuzzy 3D reality is literally just the low-resolution, lossy projection of a much denser truth. Let's take this concept and use it to solve one of the greatest mysteries in science. Section 4, entanglement as topological aliasing. We can finally replace that old spooky action at a distance idea with a brand new concept, topological aliasing. Because of our extremely limited rendering capacity, when we try to look at an incredibly dense, higher dimensional node in that static tensor network, we just can't fit its true shape into our 3D projection. So what happens? The projection folds, it aliases. It becomes a one-to-many multi-valued projection, mathematically dictated by that informational bottleneck. When we talk about this, there is really only one number that matters. Number 1. When you look at two entangled particles that seem to be communicating instantaneously across the galaxy, they absolutely aren't two separate objects talking to each other. They are literally exactly one single node
in the deterministic substrate. Which leads us to a seriously mind-bending takeaway. That physical space we perceive between entangled particles, it is nothing but a projection error. It's a thermodynamic illusion rendered around the exact same node, caused entirely by our low-resolution screen. Our finite capacity forces one single node to show up in two different places at the exact same time. Now, theory is incredibly cool, but as focused learners, we want proof, right? How do we get a concrete scientific payoff? Section 5, Testing Topological Severance. Here is the clear, actionable roadmap to physically test this deterministic boundary in a lab. First, you perfectly isolate a macroscopic system. Second, you push the complexity of that system until it strictly exceeds the local capacity bound, that COBS we talked about, of the observer apparatus. Finally, you observe what happens to the entanglement. And this is where things get super exciting, because this is the exact empirical divergence where the theory separates from standard quantum mechanics. While standard physics insists that if the system is perfectly isolated, the macroscopic entanglement will just persist forever, the finite observer theory predicts something entirely different. It predicts that the moment you hit that informational capacity limit, there will be a deterministic loss of coherence. The connection will just sever. The stakes here are absolutely immense. Our sources put this perfectly, stating, the verbless geometry strictly predicts a deterministic topological severance, driven purely by the capacity trace. Thus, the quantum paradoxes are rendered empirically testable. This isn't just a fun philosophy debate. It is a totally testable physical boundary of our reality's rendering engine. So I want to leave you with this final provocative thought. If entangled particles are really just single nodes stretched into illusions by our finite brains, if our entire physical reality is literally just a lossy, low-resolution projection of a perfect deterministic crystal, what else in your life are you completely misinterpreting? Keep questioning the system, and I'll catch you in the next explainer.